Hi guys! From the previous lecture, we learned about the mode of radioactive decay and how to determine the nuclear stable or radioactive. Today, we will learn about kinetics of radioactive decay and nuclear transmutation. Okay, radioactivity can be detected and measured by using ionization counter and scintillation counter. Ionization counter is based on ionization which produce free electron and gaseous cation which attracted to electron and produce electric current. While scintillation counter is not based on ionization but it's based on light emission where radioactive particles strike a light emitting substance and emits photons, and photons will attract a cathode and produce electric current. Okay, it is how ionization counter works. It consists of tube filled with argon methane that act as cathode and thin wire in the center that act as anode. Okay, first the emission from the sample enter the tube, strike the argon atom, producing the argon ion that migrate toward the cathode, and the electron will migrate toward the anode, producing the current. The current is created and amplified and appear as the meter reading. Okay, scintillation is based on light emission where this liquid scintillation consists of phosphor and solvent where the phosphor is a solid material that emits light when exposed to radiations. Okay, so this cocktail dissolve the radioactive sample and emit pulse of light when excited by emission. Okay, the rate of radioactive decay also can be called as activity, and it is proportional to the number of nuclei present, and it follows first order kinetic. And K here represent the decay constant. The larger the value of K, the higher the activity of the substance following the first order kinetic. Here are examples of questions that need you to calculate the specific activity and the decay constant. The information that given to you is the activity of the sample and mole of the sample. So you need to find the specific activity in unit Ci per G. So first, you need to find the mass of the sample from the mole given. So you will get the mass of the sample and find the specific activity by convert the activity in minute to seconds, and remember 1 Ci to 3.7 10 to the power of 10 V per second. So you need to convert to Ci and then divide by mass, then you will get the specific activity of the sample. Then you need to find the decay constant. So you need to divide the activity of the sample by the number of the atoms. So given the mole of the sample times with the Avogadro constant, then you will get the decay constant for the sample. Okay, half-life is the time taken for half the nuclei in a sample to decay. And we determine the half-life of nuclear reaction from its rate constant, where n is the number of nuclei at the given time, and n not here is the initial number of nuclei. From the previous equation, you will be able to determine the number half-life of the sample, and then you will get this equation half-life equal to ln 2 over k. This half-life is inversely related to decay constant, where large k equal to short half-life and small k equal to long half-life. And as we can see here from the graph, the number of nuclei remaining is half after each half-life. As we can see here, the decay constants and the half-life of many radioactive nuclei vary over a wide range. Okay, here are the example of questions that need you to find the activity and the fraction of nuclei that have decayed after a given time, and the information that given to you is the half-life of the sample and the activity of the sample. Okay, here you need to find the activity at a given time, so you need to find this equation. Okay, since we don't know the decay constant, so you need to use this formula to find the decay constant since half-life is given. Then you will get the decay constant. Substitute the decay constant into this equation, and while T equals to 59 yield and A is the initial activity given 1.2 10 to the power of 12, substitute all the value, then you will get 80 equal to this. And find the fraction decay where the initial activity minus with the activity at given time divided by the initial activity, then you will get the fraction decay. Okay, radioisotope can be used to determine the age of certain objects. Based on measuring the amount of carbon-14 and carbon-12 in biological origin, we can determine the age of object by measuring the ratio of specific isotope in it. For example, here, the ratio of carbon-14 and carbon-12 remain the same for all living organisms. Once organisms die, the amount of carbon-14 starts to decrease as it decays to form 14N. Since carbon-14 decay at predictable rate, so measuring the amount present indicates the time that has passed since the organism died, meaning that the difference between carbon-12 and carbon-14 ratio in that organism and ratio in living organism reflect the time elapsed since organism died. To determine the age of objects that don't contain carbon, different isotopes can be used. For example, potassium-14 and argon-14 ratio can be used to determine the age of certain rocks. Okay, a plot of specific activity versus time will give you straight line with a slope negative k. Then you solving the value of t, then you will get the age of the objects. Here are examples of problems that need you to estimate the age of the sample. For example, here, the information that given to you is half-life, activity at initial activity of the sample, and the activity at a given time. So, firstly, since the half-life is given, so you need to find the decay constant using this formula. Okay, using this equation to find the age of the bone and substitute the decay constants into this equation, then you will get the age of the bone. Okay, transmutation is the conversion of one isotope into another, and it caused by radioactive decay or by bombardment of nuclei with high energy particle. For example, here, alpha particle is emitted from radium and is bombarded with atmospheric nitrogen and form proton and oxygen. Of transmutation where the alpha particle is emitted from the radium and the nitrogen capture the alpha particle forming the fluorine atom, and this fluorine atom then expel the proton and become oxygen atom. This is how the isotope is converted from another isotope. The particle accelerator was invented to impart high kinetic energy to particles by placing them in electric field, usually in combinations with magnetic field. As we can see here, the protons are introduced at the end of the tube and attracted to other end by a potential difference. This process is performed in stage to achieve high particle energy without having to apply a single high voltage. Cyclotron accelerator use the same principle of linear accelerator but applying the electromagnet to give particles spiral path to save the space. It has two disks, positive and negative, and the particle is accelerated as it passes from one disk to another until it deflected to target nucleus. Transuranium is the element that have atomic number 93 and above, and here are some reactions that were used to form several of these elements.